Okay. All right. Thank you for the invitation and for also arranging such good weather on the weekend. I mean, it was just lovely. Yeah. I've had a wonderful time, and I'm going to tell you about something that we started talking about yesterday during the discussion session about a potentially new form of heat conduction in the neutron star crust. This work was done in collaboration with Deborah, Vincenzo. Deborah is here. Vincenzo is a fellow staff scientist at Los Alamos, and you met Jose and Rishi is a postdoc in Los Alamos. Okay, after Dima's talk, I don't think that I really need to go through all of this, but just let me put this up there so we have some definitions. Dima gave a very good introduction to thermal conduction in the neutron star crust. So typically we have heat flow that's controlled by this one parameter. It depends on three microscopic inputs. The specific heat, the thermal conduction coefficient, the specific heat of the heat carriers, the velocity of the heat carriers, and the mean free path. So if we just ask in a terrestrial solid or even a neutron star outer crust, what are the, we heard that electrons dominate. The electron specific heat is large. It's suppressed only because only electrons near the Fermi surface carry the heat, but still it's large compared to the phonon specific heat, which goes like TQ. And this is the velocity of these phonon modes. So if you just take this ratio, you end up with a number that's Fermi velocity of the electron squared over T squared times the velocity. So unless it's an insulator, the electrons will usually dominate. But it's important to keep in mind that the phonon mean free paths are typically very large compared to the electron mean free paths. So if we ask this question, do electrons dominate under all circumstances? The answer is no. There may be circumstances in which the magnetic field can suppress electron propagation, transfers to the field. And this was worked out, as we heard yesterday, by several people, including Dima here. And the semi-classical result is that the conduction perpendicular to the field is essentially highly suppressed by this factor here that can be as large as several orders of magnitude, where omega is the gyro frequency defined by this relation and tau is the collision time. So there are situations in which the electron conduction can be small. So this led several people to think about lattice phonon conduction in the outer crust. So they realized that mean free paths, when I say they, I'm talking about these papers here, and in particular the paper by Andrei Chuganov and Paul Hansel. And what they showed was that lattice phonons in fact can carry heat. And in this figure, you see the impurity as not impurity, the conductivity as a function of the density. And this is the electron conduction parallel to the field. And even for a modest field of 10 to the 12 Gauss, the conduction transfers to the field is suppressed. And the phonon conduction is shown in these two curves. If the only source of scattering for the lattice phonons was impurities, then in fact it could even exceed that of electron conduction, even parallel to the field. But what these authors found was that the dominant mode of scattering was scattering of electrons. And in this case, there's still some region in the outer crust where these phonons carry heat. Okay. So what about another type of phonon that exists in the deeper part of the neutron star? So if you go deeper into the neutron star, we heard about the neutron superfluid that exists there. And in the limit of a uniform superfluid, there is one collective excitation of these neutrons, which also has phonon-like dispersion relation, and it can also carry heat. Now, the thermal conductivity, if I just use the kinetic theory formula, I can write it in terms of specific heat, velocity, and mean free path. So let me now, the whole purpose of this talk will be to describe the physics of computing this mean free path. But let's just take it as some number and ask if I put in typical values for temperature and velocities, which is what I'm putting in here, what is the heat conduction I would get? So the heat conduction I would get at say 10 to the 8 Kelvin, and if the velocity of this mode was about 0.1 times the speed of light, I would get 10 to the 22 ergs per centimeter per second per Kelvin. Now, what do I need to compare that to? I need to compare it to electrons. And electrons, let's look at electrons at the neutron drip density at 10 to the 8 Kelvin. And if you did not have a magnetic field, you would get 10 to the 18. And if you did have a magnetic field of 10 to the 14, you would get 10 to the 16. So if this guy has to compete with electrons, this has to be of the order of 10 to the minus 6 centimeters. So if the mean free path turns out to be of the order of 10 to the minus 6 to 10 to the minus 4 centimeters, these guys can compete with electrons to conduct. So when I first started thinking about this, I said, oh, that's too big a mean free path. I mean, it's probably never going to work. And in fact, the first draft that I sent to Chuck said, yeah, it's not going to work. But since then, I've been trying to calculate, not use my intuition, and trying to figure out what this really is. Okay. So to calculate that, we now know that the neutron star inner crust is indeed superfluid, and the gaps are going to be of the order of 1 MeV. So if you're at 10 to the 8 Kelvin, a significant part, that's 10 to the minus 2 MeV, a significant part of the neutron star crust is going to be superfluid. Okay? So you can't excite any neutrons. All the neutrons are going to be gapped, so there are no neutron excitations. What are the low energy excitations in the system? Of course, we have electrons. You can always do particle-hole excitations of the Fermi surface. And there are always these phonons of the lattice. The ions themselves are frozen. You can't excite single particle motion, but you can easily excite the phonons. There are 3 of them, 1 longitudinal and 2 transverse. And this is something that we started thinking about. What are these superfluid phonons? This is a collective excitation of this neutron fluid. Okay. So to calculate the mean free path, we need to identify some dissipative processes. So let's just represent electrons. They're relativistic. They have a dispersion relation given by this. Then there are these phonons. I'll just call all of them as lattice phonons. They also have a linear dispersion relation, and that's the symbol that you'll see in these diagrams. And then you have these superfluid phonons, which I'll draw as a wavy line. So the springs are lattice phonons, and those are superfluid phonons. Now these velocities, as you go from neutron drip to the edge of the inner edge of the crust, the velocity of these modes will basically start at 0 and go all the way up to something like 0.1 times the speed of light.
But can you distinguish these 2 modes? Aren't they hybridized? So
there is mixing, but it's very weak mixing. Yes. So the longitudinal component of this and that mix. So that's in fact what I'm going to calculate. So so these velocities, so you'll still have, when they mix, you'll still have 2 modes. And those 2 modes will, one of the modes will look almost like this, and the other mode will almost look like that. So these velocities will range from 0 to 0.1, and for these modes, the velocity will range from 10 to the minus 2 to 10 to the minus 1. So let's look at electrons. The typical processes are electron phonon processes. And this is just an electron emitting a phonon, or a phonon being absorbed on an electron system. So this was in fact the most dominant process that Pavel Hansel and Andrei Chuginov calculated for the dissipation of this phonon mode. And then there is an electron phonon process for this. I'll come back to talk about that because that turns out to be the most important process. There's also scattering of impurities. So we heard about this also. An electron can scatter off some impurity in the lattice, and so can phonons and also these new type of collective modes. There are multi-particle processes, just electron scattering, or 2 phonon scattering of 2 to 2 processes in the phonon, and there could also be processes where a single phonon of this type decays into 2 phonons like that, because the velocity of this guy could be larger than the velocity of those guys. Okay. But in reality, the most important process is this. Now, this is an excitation of a neutral superfluid. And the way the excitation of a neutral superfluid couples to the electrons that are charged, there is no fundamental coupling other than magnetic coupling between the neutrons and the electrons. However, because there's a coupling between neutrons and ions, that will induce a coupling between neutrons and electrons through these phonons. Okay? So what this this interaction that we're talking about is in fact the interaction between these neutrons and the electrons through the phonons. So let's just quickly look at impurity scattering first before we talk about electron dissipation. So why is this irrelevant? It's irrelevant because the impurity scattering is going to be like Rayleigh scattering. Okay? If there's a typical size for this impurity, that's R0. So let's say that this is a nuclear size. So R0 is like 10 Fermis. Then you know that this cross section will be a very high power of Q because that's Rayleigh scattering. That's characteristic of Rayleigh scattering. So this number is very small, so you can ignore the denominator. And this goes by Q to the 4. Q is the momentum of the phonon, which is proportional to the temperature. So the mean free path due to Rayleigh scattering is just the number of scatterers times the cross section. So this goes as a very high power of T. Okay, it goes like T to the minus 4. So you put these numbers together, use some estimate for the impurity concentration, which is parameterized by this one fraction x. So x is the ratio of the distance between impurities to the distance between ions. So x is simply d over r. R is the distance between ions, and d is the distance between impurities. So if every particle was treated as an impurity, x would be 1. So we expect x to be of order 10 if it's a highly impure system. So even for a highly impure system, the mean free path is huge. So obviously, as we discussed before, if I have a mean free path that is of the order of centimeters, you're going to get a very large contribution. So this is not a good source of scattering for these particles.
How did you decide the strength of the impurity?
The X factor?
No.
R naught?
For example, impurity might be characterized by a Z, which is different from the average Z in the lattice. How does a tremendously different Z differ from
So I guess what would be more relevant here is to distinguish between neutron-ion scattering. How is the neutron impurity scattering different from that of the neutron lattice scattering? And I'm assuming here that that's an order 1 effect. Because if the scattering of the impurities were very similar to scattering of lattice sites, then this R naught that I would be using would be effectively even smaller. But once I realized that this was unimportant, I just said it doesn't really matter what it is. Okay, so to understand, now we want to understand how does the phonon excite electrons in this system, right? So what we basically did was we said, okay, there must be a low energy theory that describes the interactions of these phonons. So if I try to write down such a low energy theory, there's one very good property of such a theory. It's that phonons always interact by momentum dependent interactions. So they're always derivatively coupled. So if I look at just the theory of, say, phonons in the superfluid, I can write down the kinetic terms for that. And then I can also go back to the fundamental Hamiltonian for neutrons, and from there derive an interaction between the phonon and the neutron itself, and also derive higher order interactions of this sort. Okay. So this is a systematic expansion because each of these derivatives brings in something like a temperature, but this is a much higher energy scale, so it's okay to keep only the first few terms of such an expansion. Okay. Now, so this couples phonons to themselves. This would give rise to 3 phonon processes. This would give rise to a process in which a neutron superfluid mode tried to excite the neutron system. But that would be very suppressed because you can't excite the superfluid because there's a gap in that spectrum. And this here, for example, would be the coupling between the, if this was the electrons, if this was the electron field, this would give you the phonon electron coupling. Okay, now there's also a term in the Lagrangian that describes the interaction between this field, which is the excitation of the phonons in the in neutron matter, and this field, which is the excitation of lattice phonons. So this is a term that couples these two. And so we need to figure out a way of computing this parameter G mix. And there are also terms that couple one of these phonon to several of lattice phonons. So we also need to compute this coefficient. So we need microscopic physics to basically find a way to compute those things. Okay, so this may be familiar to most of you, but just as a reminder, how do you go from a fundamental Hamiltonian that has particle degrees of freedom to some collective degree of freedom? Okay, so there's a very simple derivation that you can find in Federer and Velechka, which shows that, okay, so we have an interaction here between electrons and ions. So this is the electron field, and this is the ion field. So this is just like a density operator for the ions. Now, the ions are all frozen into some lattice sites, so I can always write this as the ion density, which is the density of lattice sites, and a small fluctuation. Okay, so this small fluctuation is the one that gives rise to the phonons. So how do we? So we now need to express this small fluctuation in terms of displacement field D, which is the displacement of every ion from its equilibrium position. And you can very quickly realize that the only way you can change the density is if this displacement field D had some spatial variation. If it didn't have any spatial variation, it just moved the lattice. So that's not a phonon field. So you can a change in density comes from a gradient of this. Okay? So you work through the algebra, and then you need to find a way to redefine this field, this displacement field, which is just the phonon field, so that the kinetic term that you write down for this field is normalized in the usual way. Okay? So that this factor just comes in as a definition. Once you put this factor back in here, so you want to replace this in terms of this field, you very quickly get to this point. So once you replace this field by the gradient of D field and a redefinition, which is just a constant in front of it, you end up with a form like this, where you see what I was talking about earlier. There is some low energy constant that appears here that has all the microscopic physics that comes from this interaction V. Then you have a product of these two fields, and then you have a gradient of this phonon field. Okay, so that's why the coupling is derivatively coupled, and then there's some constant. This constant is what I was calling as F. Okay, so this is fairly standard, well-known procedure in condensed matter physics, and we just adopted it here for this problem. You can also now couple neutrons to lattice phonons in exactly the same manner, but now you need a different interaction. In the previous slide, this interaction was the Coulomb interaction, but highly streamed Coulomb interaction between the electron and the ion. So this was essentially a short-range interaction. And again here, we're going to have a short-range interaction between the neutron and the ion. And very little is known about the interaction between neutrons and ions, especially very neutron-rich ions. So as a first guess, let's just use a scattering length between neutrons and ions to characterize this potential. So if I use a scattering length and I look at neutron scattering lengths on nuclei, terrestrial nuclei, which are very different from nuclei in the neutron star, but nevertheless, let's try to get an order of magnitude estimate. You find the typical size for this scattering length is of order 10 Fermis. Okay, so these are scattering lengths for various nuclei scattering of neutrons. So you go through
this.
this.
Is just the nuclear size, right?
Yeah, it's roughly, that's what it's going to be.
Because the no.
Unless, my worry was there would be some low-lying resonances and things like that.
Yeah, but I mean, you have a lot of these things, but the basic scale is set by that.
Yeah, I agree. That would also be what you'd expect from the nuclear size. That okay, the typical number you want to put in there is 10 Fermi. We put that number in, and now we have an interaction just like the previous one, but between a lattice phonon and neutrons. Okay, so this 1 over f, which is the low energy constant here, can be now related to more fundamental constants of this interaction. Okay, so I think we have basically everything that we need to go ahead and construct a theory to calculate dissipation. So these were
Can
the
I just ask, what would generally be a lot of S-wave resonances within a few MeV? I mean,
so
what? Well, just take ordinary old nuclei. Don't worry about the fact that they're neutron rich.
Right.
But
So yeah, there are. It very much depends on whether or not a bound state exists for the nucleus.
because we
So-
know that from ordinary nuclei.
So if you ordinary nuclei,
This dead-ends a lot of things. States. Now, why should it be any different for?
I think in the main reason I expect it to be qualitatively different in the neutron star cluster because each nucleus has filled every neutron level that it can potentially fill because it's neutron driven. So there are no additional bound states in there in that nucleus, right? So this is so neutron rich that there are no bound states left.
Yeah, but there are ones which are just.
But there are no lines
Just
of
above
resonance.
Yeah.
You're a neutron drift, there's neutrons are hopping on and off, there's lots of levels, right?
Yeah, but
Zero energy.
the lots of levels at zero energy, so you still want, you still want to be able to have some kind of effective interaction. So in fact, this.
But it doesn't. But the fact that there are many resonances, when you say that this effective interaction is changing sign like crazy as you go just above threshold here.
So that's true. But what I'm trying to get is a magnitude of that size, right? How large is that neutron ion interaction?
Yeah. Okay. Then the question is what you want to do with it afterwards.
Right.
Because if you want to average it, you get nothing,
Right.
right? But if you if you square and average it,
Yeah.
maybe that's better. Give you something.
Yeah. So I suspect that the area where we're going to really need to invest more investigation, more time in trying to figure out whether this estimate is correct is in fact precisely trying to figure out what is the correct potential to use for neutron ions in the neutron star crust. Okay. Now, one thing is to just say, okay, I'm just going to take some kind of a simple model for the scattering length and assume that this number can go between -10 and +10 and just do a calculation, right? So in the end, the only thing that's going to matter is a squared. So if I assume that a of order 10 is a reasonable guess, then I can proceed, and that's precisely what we tried to do. Things will get really bad if a is of order 100, but I can't see of a way in which you can arrange that. Okay, so if I take a of order 10, I compute these coefficients. Now I know a way of coupling the lattice phonons to the neutrons, but I also know a way of coupling the superfluid phonons to single neutron excitations. So I basically have to now integrate this loop to get an effective coupling between these two modes. Okay? This is a very short distance physics, so I end up getting this, and that's shown here. And I look at a diagram like this to compute this coefficient, where I couple one superfluid mode to two lattice modes. At the end of the day, I get numerical values for these coefficients, which I find to be 10 to the -3 and 50 MeV. What it's basically telling us is that this coupling is weak. Okay? And it's also telling us that the scale at which you can ignore higher order terms is very, very large. So it's telling us that this expansion should truncate pretty quickly. So both of that I think is good news because yes, we can change this around a little bit, but if this is less than 100, this is still going to be much less than 1. So how do I calculate dissipation? So essentially, if I had no dissipation at all, as Chris was pointing out, you would have oscillations between these two modes. and they would propagate just oscillating between them. However, we know that lattice phonons are coupled rather strongly to the electrons. So this mode doesn't propagate very far. So as it oscillates, this mode oscillates into a lattice phonon, but the lattice phonon has a finite mean free path, so it begins to decay. So the way this decays is essentially through oscillation and then excitation of electron mode pairs. So in other words, if I knew what the mean free path of the lattice phonon was, through this mixing, I can express the mean free path of the superfluid phonon in terms of the mean free path of the lattice phonons. Okay. So people are, especially in the paper by Chugunov and Hansel, they had computed the mean free path of the lattice phonons. So we have that ingredient here, and then we went in and put in the rest of the factors. And what we found quickly was that if you're very far away, of course there's going to be an important point where the speed of this mode becomes equal to the speed of that mode, and there will be a resonance. But as long as you're far away from that resonance, the mean free path of the superfluid phonon is about 10 to the 5 times the mean free path of the lattice phonons. So these guys propagate a lot longer distances than the lattice phonons, mainly because this mixing was small. Okay, so this is a plot of the mean free paths of this phonon mode, and you can see this is neutron drip, so that's where you start. What's interesting is if you look very closely at this curve, there is a region where the gap is comparable to the temperature, but that region is minuscule. So in this, when superfluidity just sets in, these phonons don't go very far. They very quickly decay into making these neutrons. But that's a very tiny region. So there's an exponential growth of the mean free path, which you don't see here, but that's over a very small range. And then you see a rather large mean free path. So the reason you have large mean free paths here is twofold. One, you're far away from the resonance, so there's very little mixing going on between these two types of phonons. And the other reason is that the number of phonons is inversely proportional to the velocities, q. So if these phonons have very small velocity, at a given temperature you have many more of them, right? That was basically the number density was going like t cubed over v cubed. So that's one reason why you have a lot of the specific heat is large here, and they will also contribute to the mean free path, to the conductivity. The other feature that I've already mentioned is that when it comes close to resonance, of course, now it's very easy for this for the lattice phonon to turn into for the superfluid phonon to turn into a lattice phonon, and then it very quickly decays, so they don't get to go very far. Okay, but anyway, we are finding mean free paths that are somewhere between 10 to the minus 4 and 10 to the minus 6 centimeters, which will make you think that yes, this could be relevant based on some of my earlier arguments. So this is the thermal conductivity of all the components that we've been talking about at 2 different temperatures and for 2 different magnetic fields. Magnetic field of 10 to the 13 Gauss and a magnetic field of 10 to the 14 Gauss. So the conduction parallel to the magnetic field is independent of the magnetic field. So this is the electron conduction parallel to the field as a function of density. So this was the lattice phonon contribution calculated by Chugunov and Hansel, and this is the contribution that we calculated. So at neutron drip, you're very far away from resonance. You have a lot of thermally excited phonons. So in fact, surprisingly, we find at 10 to the 8 Kelvin that even without magnetic fields, there's some tiny region where this phonon transport seems to be important. But as you go deeper, you get closer to the resonance, this coupling gets strong, dissipation also increases. So in this region, for most of the crust, the superfluid phonon mode remains important, but is not competitive with the parallel conduction. So it is important for conduction perpendicular to the field. Now that's especially true if you look at this figure, right? So here the phonon conduction is very temperature dependent because the number of phonons is very temperature dependent. Here you see that the superfluid phonons are unable to compete with the electron conduction parallel, but can be more important than electron conduction transverse if the field is 10 to the 14 Gauss. Okay, so that's basically the main message, that, you know, this phonon mode, if you have large magnetic fields, this phonon mode can be important. And from this figure, you would also guess that maybe if the temperature is very high, even without magnetic fields, maybe the first 100 years of the neutron star evolution, when it's trying to go from 10 to the 9 to 10 to the 8 Kelvin, there could be a phase where these guys are important if the gaps are large. Okay? So that's, you know, I would say the main message. Now, I want to briefly mention, I'm my own moderator, but how much time do I have left?
Well, rhetorical question.
No, actually, the moderator is sitting right there. According to long arm.
Okay, so I want to talk about two things that are not in the paper, which I think are also interesting. And that has to do with entertaining the idea of very large magnetic fields. So imagine that we have magnetars, very large fields, and you say, okay, I'm allowed to put electrons in just a few Landau levels. Okay? And if electrons are only in a few Landau levels, and I try to excite this electron gas, there are going to be all kinds of restrictions on the amount of energy and momentum I can transfer to this electron gas, because they're in highly discrete levels, and they have only free momenta along one direction. So what we did was we calculated, if I put all the electrons in just the first 3 Landau levels, and I asked what angles at which the phonon must propagate in order for it to actually transfer energy to the electron system. So this is Q perpendicular, Q parallel and Q perpendicular. And if the phonon was propagating in any direction that is not shown by these curves there, it's unable to excite this electron gas. So that's interesting, because now we're saying, we started out with the fact that phonon propagation would not care about the anisotropy, and they would be, you know, they would float easily. But now once you start putting electrons in a few Landau levels, you only have special directions in which there's dissipation, and in other directions there is no dissipation.
Naive question, this is the lattice phonons, not the superfluid phonons?
So it doesn't matter. So this would apply both to the lattice phonons and hence to the superfluid phonons, right? Because they dissipate in the same way.
But you might need a gigantic field to quantize it, densities in inner crust.
Yeah. So this here is really talking about the outer crust. Right? If you want to quantize the electrons in the inner crust, you might need 10 to the 16 Gauss. Yeah.
And why there are 2 regions?
Yeah, so that's because there are several levels occupied. There are like 5 or 6 levels occupied. Okay. So the electron hole excitation spectrum looks like this. There's a small region here and a small region here, which is corresponding to these two. So if you look at the polarization function as a function of angle, you see that. So bottom line is, if I'm calculating the phonon mean free paths transverse to the field, then in the outer crust of a neutron star, the electron, the lattice phonon may be able to propagate even further than what Powell, Hansel, and Andrei Chuganov found in their paper. So it may be more efficient than what they have done.
Sorry, and how did you calculate the polarization function?
So the polarization function for electron gas in a magnetic field, the imaginary part of this, we calculated it, you know, just using the propagators for electrons in large magnetic fields. Right. So you had calculated the real part of this to calculate the screening. And we in very similar way, we can discuss this later. In a very similar way, we
So
calculate
this is usual polarization
of electron,
yeah.
very standard electron polarization. So this is something okay. But most of it comes just from energy and momentum conservation, which is what. Okay. So one last thing, and I'll quit. This has something to do with screening in very large magnetic fields. Okay, so dissipation in large magnetic fields is anisotropic. What about screening? We know that the electron screening for ions is very important. We heard from Chuck and several others about the screening length set by the electron Debye screening. So we know that, so you have ions interacting with the Coulomb field, but the Coulomb field is modified because the electrons screen the interaction between these ions. And so the potential between two ions with charge Z is given by this expression, where typically we say that this function g of r has a form like this. That is the Debye screening length. So if you have a very large field, so I've just stuck in a huge field of 10 to the 15 Gauss, and instead of density, I just look at the electron chemical potential. Okay? So if I go to higher electron densities or higher electron chemical potentials, the screening length, if I had zero field, would behave like this. But when you have a finite but large magnetic field, you see this very interesting behavior which kind of follows this as you go in. So this is basically saying that the magnetic field is all the electrons are in just one Landau level here. The first two Landau levels are filled, 3, 4, and so on. By the time you fill many levels, it becomes almost like a simple.
It will be washed out by the temperature.
Yes, if the temperature is comparable to the splitting between those. Okay, so this is standard. You would expect this. This has already been published. Nothing new. What is interesting is if you go and you ask carefully the question as to whether the long distance behavior of this screening is actually exponential, you find that it's not true. Again, well-known condensed matter phenomena, that at very long distances, if you have a sharp Fermi surface leads to these kind of oscillations in the screening function g of r, and these oscillations are called Friedel oscillations. Now, usually Friedel oscillations are unimportant in relativistic systems because the Friedel oscillation amplitude goes like mass of the electron divided by the Fermi energy. Now, if you have a large field, even at high density, you can have a small Fermi momentum. So essentially what that means is that the amplitude of these Friedel oscillations can be large. So if you're looking at the outer crust of a neutron star, the long distance behavior of the Coulomb potential between ions will be very different, and it can affect properties like breaking strains and shear modes in the outer regions of a neutron star. Okay? So this is something that's, just the physics is here, but to see how it impacts neutron star physics, we'll have to do some work with Chuck on putting this potential in an MD simulation.
I guess it's not even a spherically symmetric potential.
No, actually, absolutely.
Right.
So this is
not just a function of R.
yes, exactly. So I forgot to mention that. So this is the potential. This is the potential along the z direction. Oh, sorry, along in the transverse to the z direction. And this is the potential. So there are no Friedel oscillations in the transverse direction. It's only along the magnetic field. So it's a very anisotropic function. Only the anisotropy is driven only by this Friedel oscillations. If you kill the Friedel oscillations, surprisingly, there is no anisotropy. Okay. So those are the things I wanted to share with you. Moderator can then continue.
In your model, if one would consider pure neutron matter, your collective modes would have infinite mean-free path.
Almost.
But in principle, in nuclear physics, the collective motion will have some damping due to mixing with complicated states.
Right.
Not the
So
approximation.
in uniform neutron matter, the only dissipation would be phonon-phonon scattering, which is very weak. So there are no other modes to excite, right? I mean, in a nucleus, it's very different. There are so many low-lying surface modes. There are ungapped modes in the system, so you can excite. I mean, if you just take the hypothetical case of pure neutron matter that's superfluid, you know, it's going to have very large, very large mean free paths. That's kind of the helium liquid example.
The results for the thermal conductivity of the superfluid phonon,
Yeah.
how does that depend on the properties of the pairs, the gap, the coherence length, or other properties?
Okay. So if the gap is large compared to the temperature, it's very weak. Okay. So that's, so in the language of the low energy theory, the gap parameter does not enter the low energy coefficients till you go to much higher order. So when the temperature, when the energy carried by the superfluid phonon becomes comparable to the gap, that's when things begin to change. So knowing the gap is important only when the temperature is comparable to the gap.
What other properties?
Like the velocity depends on the properties of neutron matter, right? The velocity is just, in the free gas case, you would write the velocity of the free gas. So we want the velocity of this superfluid mode is just kf over mass of the neutron times square root of 3. But in a strongly coupled case, like at unitarity, for example, if it's a, then you get, you know, changes to this. So if you knew the equation of state, and this would be, you know, square root of dp d rho. So if you knew the equation of state, then it would affect things like the speed of this object. Yes.
When you calculated this thermal conductivity of superfluid phonons, you took typical frequencies equal to 3.
Yeah, that's right.
Is
So
it possible to calculate the resonant mean?
yes, it is possible. We are planning to write that up in a bigger paper, which has been in preparation for a long time. Yeah, no, it's true. I mean, because the mean free path is so energy dependent, you would imagine that the lower energy phonons would travel even further. So doing this average properly is important. Yeah, no, we'll do it. Yeah, I know you mentioned this. I feel bad because you've already mentioned this some time ago.
Really?
Well, I guess as long as the other average converges, then it's probably definitely produces numbers. I mean, what would be interesting if it diverged, then you could be in
But
trouble.
it can be a factor of 5 or 6 or something like that.
Yeah, if I do it just for phonon scattering, that integral diverges.
Yeah.
But for phonon electron, it doesn't.
But it diverges with arithmetic or something like, yes, slowly diverging function. As far as the,
Yeah, that's why it's scattering.
Yeah.
I think it's important, we talked a little bit about this, going to the cross-cooling data and saying, if I arbitrarily turn up the superfluid thermal conductivity, at what point would it be in disagreement with the data if you enhanced your mean free paths by factors of 1,000 or something? Like what's the what observational limit could you place on the superfluid phonons?
So I think this is the conductivity of a nearly pure electron gas. I think the impurity fraction here was very small. So that may be similar to the calculation that Sterner and Yakovlev did for crust relaxation. And they find good agreement, right, with the time scale for the scale. So if we just say I'm wrong by an order of magnitude in the optimistic direction, pull this up, right? So by some fraction of the crust is more conducting, 10 times more conducting than the electrons. Yeah, we can certainly do that. I think Danny
Dan plans to do that.
Can I just make a remark about coupling to the nucleus? I mean, one way to estimate the effective optical potential is just to ask how the energy of a cell changes when you change the neutron density. So from the standard calculations to determine equilibrium, one can get these things.
That's right. So,
Just the deformation potential.
yeah, that'll make, that'll give us a better estimate of that A, what the effect is.
Everybody's hungry, I suppose. Break for a lunch. Meet again at 4 and discuss it further.